Hello everyone, I'm Darshi Jayasuriya. I'm a doctoral candidate at the University of Auckland. And my research is towards automated updates of software dependencies. And I'm supervised by Dr. Kelly Blinko and Dr. Valeria Tarangi. Just to give a background on what a dependency is, so a dependency can be a package, library, or a module which consists of logically related classes or modules that are deployed as a separate package to be used by other entities. So through this research, we'll be looking at external dependencies mainly, and dependencies are used basically to accelerate the development process as they are already developed. Modules that can be reused by other software. And why is it important to update dependencies is because, like any other software, dependencies also come with their versions, which consist of new features, of performance optimizations, of issues fixed, which contain in their previous releases. So the motivation behind looking at the dependency update was, according to the software risk analysis report in 2021, it was reported, according to the code bases that they reviewed, that 84% of these code bases contained at least one public open source vulnerability, as well as 85% of these code bases contain open source components that are 4 years out of date. And also research states that the developers are unaware of the threats that come with using these open source software, and added to that, software developers consider it as an added responsibility to their day-to-day tasks to update dependencies as it might be out of their scope to the current development. And what is the problem in updating dependency? So updating a dependency might not be always just making the version number change. It can come with breaking changes. So what are the breaking changes? Can be the incompatibilities between two library versions. So for example, if a particular software was using version 1.6.0 of a particular library, and they were updating it to 1.7.0, it can incur some of these incompatibilities, and these incompatibilities will evolve as the library also evolves with their versioning. So in general, the incompatibilities can be categorized into 3 sections as source incompatibilities. And source incompatibilities can be like change to the meta signature, like change in return type or change in the parameters that are passed. And these kind of incompatibilities can be detected when you're compiling your code because it comes with compilation errors. And binary incompatibilities are similar to source incompatibilities, and they are also some sort of can be detected due to the changes in the meta signature. This can be source compatible, but if you haven't compiled them before linking these binaries, even though it's a child class of the collection, like in this given example, you can come up with binary incompatibilities when you combine these executables. And the final incompatibility is behavioral incompatibilities. It keeps the API signature the same, but it introduced more complex changes to the logic of the method. For example, this was a simple if condition that existed in the prior version of the library, but they considered in adding more complex if-else conditions, adding more control statements to the existing logic in the program. So these are behavioral incompatibilities. So research states that the impact of behavioral incompatibilities is higher than source and binary incompatibilities. So research has been done on this area, like to detect breaking changes using static analysis tools and detecting changes that breaking changes that are applied in client projects, and trying to automate the library version updates in client projects. That is by just updating library version number, but if there are incompatibilities, the developers have to take care of it, and also automatically fixing breaking changes in client applications, and these research are limited to the source and binary incompatibilities at their own limitations. So what we looked at the research gap was there was no categorization of like a high level categorization of breaking changes, including the behavioral ones. And we wanted to identify patterns of behavioral breaking changes because the literature did not support that, and also to automate the dependency updates containing behavioral breaking changes. So in order to address those research questions that we're looking at what are the types of breaking changes that can be introduced between two versions of the same library, and why are project-specific fixes needed, and identify the characteristics of these project-specific fixes, and how breaking changes can be automatically repaired across an ecosystem. So the approach that we will be taking to address these research questions is first to collect a set of projects that contain outdated dependencies, and then try to update the dependencies that are included in these projects, then analyze the failures that we might encounter when we update these dependencies, and develop a taxonomy based on the analysis that we have. Next, we'll be looking at why project-specific fixes are needed. And for that, based on the repositories that we have already collected, we'll be looking at the breaking changes they have introduced when updating the library and the fixes that have already been applied, and analysis on these fixes, and hopefully, based on the analysis results we get, we'll be able to find some patterns based on the code updates that have been applied. And then how breaking changes can be automatically repaired. So based on the patterns that we will be extracting in the second step, we'll extract those code characteristics as features, and using these features, develop models and try to validate them using open source software. So I'm currently in my second year in PhD. So during the first year, we were able to gather some projects with outdated dependencies, update the dependencies, and also extract breaking changes. And we also looked at projects that already have updated dependencies and have applied changes to fix those breaking changes. And during my second year, we're currently analyzing the breaking changes that we have extracted and trying to develop a taxonomy based on those breaking changes. So the methodology and the findings what we have gathered up to now is we used the libraries.io dataset, which was published in 2020, and based on that we used repositories that were available on GitHub. And for this research, we're focusing on Java projects which are using Maven as their go-to. And using Maven commands, we were able to successfully compile projects without tests. And for this, we used Java version 8 and 11. And we were able to successfully build around 3,000 of these repositories. So based on these repositories, as you might know, in Maven, a repository can contain multiple child projects. So it can be so these projects are uniquely identified as Maven artifacts. So there can be a parent artifact, and those parent there can be multiple child artifacts. So these child artifacts can also contain their own dependencies. So to extract these dependencies, which were on these 3,000 repositories, excluding transitive dependencies, we analyzed 18,000 Maven artifacts, and from those artifacts, we were able to extract around 163,000 of these dependencies. So then to look at how many of these dependencies are up to date. So we used Maven commands to get the latest versions that were available for these Maven libraries. And to create these updates, we use a semantic versioning scheme, which says that if you change the leftmost number, it will be a major version update, which can introduce breaking changes. But if you update the middle or the rightmost number, it will be a minor or patch update, which ideally should not contain any breaking changes when you update these versions. So based on that, on the dependencies that we extracted earlier, around 44,000 of these dependencies were up to date. For 26,000, a patch update is suggested, and for 54,000, a minor update, and 37,000, a major update was suggested. So based on these updates that was suggested, we built these projects based on the versions that were suggested, and found out that for the artifact and the parent artifact, around 15,000 of those dependencies fail, which gives us a set of error, like when I say we build them without tests. So we were interested in looking at the compilation errors. So between the current version that is used in the dependency and the latest version, there can be multiple other versions that were released. So since we needed to target the breaking version that was introducing the incompatible changes, we looked at the Maven versions that were released between the current and the latest version and tried to update them incrementally to detect the breaking version that introduced incompatibilities. So based on that, we identified that the breaking changes were introduced in the latest version for around 2,000 of these dependencies, and the breaking version prior to the latest version was available for 30,000 of these dependencies. So based on the compilation error logs that we received, we analyzed them, and these are the top 5 occurrences of the compilation errors. And we sampled the compilation errors that we got. So there were 95 types of different compilation errors that we identified. And we manually analyzed these 95 types of compilation errors and saw that the most common case of library change that was causing the compilation errors was due to the change result type of a method in class, which was around 5.5%. And the second most was deleting an entire API package, which would result in deleting all the classes and methods that come into that API package itself. And the general changes that was causing these compilation errors was due to transitive dependency changes and incompatibility with another library or Java version incompatibilities in general. So these are all related to this first incompatibility analysis, which can be detected using compilation errors. So we next went a step further into analyzing the behavioral incompatibilities. So based on the repositories that we already had, and when we updated dependencies which were passing successfully, we looked at those projects and identified if they contain test cases or not. So we were able to successfully get 7,000 artifacts, which included test cases. And for those artifacts, we were able to update the look at dependencies, which was around 27,000. And we updated those dependencies and built with the test cases itself and found out for around 18,000 instances, the test cases were failing because of these dependency updates. So for the categorization of the behavioral incompatibilities, based on the test failures that we found out, we categorized them into assertion-related failures and exception-related failures. So the exception-related failures will be further categorizing as the library code at the crash point and the library code in the crash stack itself, or the library code not existing in the crash stack, but it can be the client-related code or can be a transitive dependence-related code in the crash stack. So we haven't analyzed this crash stack yet, but there are multiple exceptions, around 40 of them, that are existing in this crash log that we have detected up to now. So we tried to analyze manually some of these assertion-related failures. So the general reasons were due to transitive dependencies or the dependent libraries have to be updated together. But the specific ones were everything related to Java, basically adding a new condition, using new fields, changing the logic internally of the method. So we wanted to get a more generalized idea of what sort of changes might be occurring in these libraries. So the next steps are, what we're trying to do is extract the library methods that are invoked during the test execution, and then identify the changes that have been applied between the methods that are in use between these two library versions, and try to analyze or detect patterns that result in the changes that incur these behavioral breaking changes. And also, based on the analysis results that we get, we're trying to analyze which sort of changes need to apply which require project agnostic fixes. And based on the results that we have, we might be able to apply the same set of changes that have been applied in one project to another and see if we can generalize these fixes that can be applied for fixing breaking change. And there will be manual analysis on the results that we get to analyze the code characteristics that can be extracted to as patterns in the next step. And there are tools like FixMiner, which can be used for pattern analysis, like to extract what sort of changes, is it variable change, method change. And then based on the results, we're hoping to do a thematic analysis to understand the type of changes. And based on the analysis features that we get, for a set of breaking changes, we are focusing on behavioral breaking ones for this particular step, and trying to develop a proof of concept into what sort of automatic changes can be applied, or at least provide a guidance on letting the developers know that there are potential breaking changes on the library versions that they're going to update, and hoping to validate them on a set of open source projects by actually compiling the projects and using the test cases that exist in these projects as regression test cases. So in summary, we are hoping to develop a taxonomy of breaking changes, identify when project-specific fixes or project-agnostic fixes are needed, and to automate the library update process by providing patch updates or guidance to breaking changes in the versions. So this project is funded by the Royal Society of New Zealand, and this is summarization of the work that I'm hoping to do. Thank you.
So thank you so much. I think this is a very interesting project, and these dependency errors is very annoying in Java, but perhaps even worse in JavaScript, where you may not actually get a error message at all.
Yeah.
Just shows as a bug during runtime. I was wondering about one of the first slides. So you present the semantic version.
Yes.
Numbers where we have a minor increment would be just adding new functionality, and major increment would be breaking functionality.
Yes.
So in one of the first slides you had like going from 1.5 to 1.6 to 1.7, and at some point there was some breaking changes. So in those cases, why did they not implement the major version? Were the developers not aware of breaking change?
Well, research state that even though the semantic versioning scheme is there for developers to comply with that, in order for the clients who are using the libraries to make note that there can be potential breaking changes. One research state that 72% of the libraries out there actually break this semantic versioning scheme by introducing breaking changes in either the major or the patch updates itself. So we did an analysis on the patch, like the updates on this and the compilation errors that we detected, and found out that the patch and mine update actually provides more breaking changes than the major update.
Wow.
Yeah.
Wow.
Wait, can you say that again? You said there are more breaking changes in the minor and patch?
Added together?
Not necessarily proportionally.
Yes.
Okay.
Based on the compilation errors that we detected in our code.
But I guess you will also have many more minor updates than major updates, right?
Not necessarily.
Okay.
Yeah.
Do you think maybe it's because if people release a major update, they think maybe more hardly, more about what they're breaking, versus if they're releasing a minor update, they're just like, it's gonna work.
Oh, it's still surprising.
I mean, a major version also doesn't have to contain a breaking change. Right?
Yeah,
Like, especially these days, there are so many programs that just increase the major version, like basically at every hour there.
So wait, follow up on that. Could this number, could this be, or maybe is there some systems where, in some languages where this is actually type checked or somehow verified that you cannot increment, you have to increment the major version if you are breaking something, at least that's type level. that an approach, or does that exist already? Or-
I'm not sure to answer that question, sorry.
Like Haskell has like a similar but different version scheme.
Okay.
There's always fights about it's very strict. There are, I think, some automatic tools to check, and it's very much related with types. But the difficult questions are always the semantic changes.
Of course,
not
that's really hard to check, yeah.
Good question. I've done a lot of software engineering in the past. One of the approaches that I ran across not too long ago was kind of recommendation that instead of introducing your dependency in the class itself, you should interface your dependency. So you make like, here's an interface for my dependency, and then you can test this. If you upgrade the dependency version and you have maybe unit test for your interface and they say that this feature is no longer available, your test will fail, and that way you can know if your dependency upgrade is going to break your system. So I'm wondering what your thoughts are about this kind of approach. Is there any sort of general approaches that would help facilitate upgrading dependencies?
So you mean the interface would be on the client project end?
Yes.
Oh, so okay. I haven't encountered that particular scenario that you're referring to, but it would be helpful because what we noticed during the manual analysis of the assertion-related failures was that the breaking changes or the behavioral breaking changes was not mainly introduced in the method that it was directly calling, but it was like down the line on the method calls, it can be the 10th or the 100th method that is calling. So yeah, it would be great if we can say pass the same parameters as you say in when you're implementing an interface that the method is calling to identify if there's breaking changes. But the projects that we analyzed did not use that kind of interface, maybe because mainly the repositories that we were looking at were open source repositories. And maybe client-related repositories might consider doing that. So yeah, I'll have a look at it, but I didn't encounter the scenario that you're talking about yet.
So, if I understood this correctly, you basically stopped if you tried out the version and everything worked, or didn't work.
Yeah.
And the previous one kind of worked to find like the transition to it. But what about cases where there was technically a breaking change, but that was a bug? So a few versions later they corrected that bug, and everything's working again now. Like, did your study deal with this in any sort of way, or?
No. So because the static related breaking changes have been analyzed in previous research, and what we're targeting was to try to identify a taxonomy for the behavior breaking changes. So we're trying to analyze what sort of changes that developers actually apply to that is causing behavior breaking changes or not. But we didn't actually check if it's bug related or not yet.
So, like in many languages, like for the, for example, in a library, the developers can actually specify bounds for their dependencies, right? So basically, like for this dependency, it cannot go beyond this minor version, or cannot go below this version, right? So when you apply that automatic update, do you respect that constraint?
So you to automate the process, yes, I would have to take those into consideration. So that would be on the final research questions that I'm hoping to achieve in my last year of the PhD. But to look at what sort of breaking changes we might encounter, and just making sure that it is updated to a different version itself that might actually cause compilation and resolve behavior breaking changes to identify what the changes are.
Yeah, first of all, this is really cool work. I think this kind of empirical study is really important to understand in the software engineering process. And of course, I work on the tool side, so I'm also very interested in terms of motivating tools and language work, which you're hoping to do as well. With respect to that, I'm interested in, how you'll come up with fixes, how you generate fixes automatically, how you validate those, and all those questions about designing kind of the next part of the work. And I realize you didn't have a lot of time to talk about that, but actually one specific question I had was you talked about maybe mining fixes, right? And that can help with libraries that are and patches that are widely used and are causing problems for people already. But what about when a new patch comes out? I can't mine anyone who is using it. So can it help with new code?
So we were looking at mine patches to extract patterns that can occur, that introducing behavior breaking changes. But if we can encounter those sort of patterns in the versions that are going to be updated, we might not need the mine projects to be updated to mine those
Okay, so the
patterns.
pattern generalizes.
Patterns,
perhaps. Yeah.
Because it's a broad topic, and we're not hoping to achieve all the compilation errors or all the exceptions. So as I said, there are some like 40 odd exceptions that we encountered while analyzing these test failures. So hoping to start at the initial point, looking at preconditions or control statement changes, maybe, which might be able to fix. So those are the initial steps. The initial things that we're hoping to look at.
Yeah, okay, cool. How will you know whether you're successful?
Yeah, so hoping to test this on open source software, so it's still, we have to like look at projects that are using like have test cases and actually invoking the potential library function that we are looking at. So we might come across a small set of samples like that, but that's the goal.
Okay, and what metrics would you gather that might show that you do well with those updates?
I mean, I'm not sure yet, but hoping to, as I said, based on the test case passing or failing levels, we might determine that.
Can you convert more programs to test cases, more test cases succeeding after an update than do right now, or than do without your cases?
Yes, potentially yes.
Yeah. Oh, okay. So more to think about, but that's part of the point of this.
Yes. Thank you very much.
Thank you then.